Hello, Matt. So far, it's just you. Oh, spoke too soon. Got another one. Got two people now. Anybody have any questions while we're waiting for people to show up?
I don't think so. Let me go take a look at the homework and make sure I didn't have any questions about it.
Gotcha.
What day's the test two due?
I think it's the 25th of September. So
Did you open up test one? Because I haven't seen it open.
Oh, that was for you. You missed it, right? I thought I did that already.
I thought it was me and someone else.
Yeah, it wasn't just you. I mean, but yeah,
I think you said that you'd give us another week last Thursday.
Yeah, I thought I opened up. Let me double check. It appears that the practice test September 11th was the last it was due. So no, I did not. So let me do that right now while I got you here so I don't forget. And of course it wouldn't hurt if I did this, make sure I got the right people. Yeah. Wait a second. It said you did do test one. Matt.
Sorry, it says I did test one.
Yeah.
Oh no, I think that was me. I know I did test one.
Oh, is that Matt? Okay, you were talking. Oh, Nathan, that's what it was. Gotcha. I thought Matt. It's got a green box around Matt's name, and I didn't recognize Nathan's voice, so that's why. Yeah. Sorry about that, guys. Yeah, that makes a lot more sense now. I was saying, why does he want to do it? He don't need to do it, Craig. let me fix that real quick. Sorry, Nathan. So I'm looking at the quizzes now, and I am going to give you, will the 19th be sufficient for you?
I think that was yesterday.
Oh, it's you. Yes, it was. The 25th be acceptable?
Yes.
Okay. So I'm going to do that now. Yep, I didn't make a special one, so I don't know. Maybe I did the wrong class or something. I don't know.
Professor.
Yes.
I emailed you last week about taking a test because I wasn't able to.
Yeah, I'm doing that right now for you as well. You're Arnold, right, or AJ?
Yes.
Yeah, I'm making it due the 25th. I'm making the practice test open till then as well. So if y'all need any more last minute practice, you should be fine to go. Yeah, I just did the test. Now the test or the practice test. Now the practice test is available. Now I'm going to do the test, and you should be good to go.
Appreciate you.
No problem. Sorry about the delay. Maybe I'll be a little more generous since I forgot and not take the whole 10 points off. So let's see. Need that guy. And I need that guy. Tom Hanks. Okay, now both of them are set up. So let me know if anything goes on. I'm still here if y'all have questions in the meantime, all that good stuff. So, all right, we got another student coming. It's a good day. We got 4. All right, so yes, test one's available again. I now got 4 of you guys in here, so I guess we can go ahead and get started. I essentially completed all of chapter 24 last time. There was that one example I didn't get to do, but I have done that on my YouTube channel. Hopefully you guys found it. I think I even went back and put a link to it in my modules. So it should be there. I just opened up the module for this week, and homework for chapter 25 is there. I might put some more links. Now, my plan was this weekend I was going to work some problems for you and post them, but actually turned out that Wednesday night my course didn't save that I did online. And then Thursday, your course, I discovered that it wasn't saving because somehow my computer all of a sudden changed my permissions to me not having permission other than to read my own hard drive and my own external backup hard drive. And I'm still having a little bit of problems with that, but that's what's going on right now. So I'm hopefully that'll all be taken care of. This meeting should be in fact done and recording here, which means I can post it tonight. And the Thursday one, I posted it to the cloud. So I just got to find enough time to download it from the cloud and then upload it to YouTube. So hopefully that'll happen. Let me double check, make sure this one is recording to the right place, because I did that one to the cloud last time. It's not letting me go there. Okay, it's doing a local computer, so that's cool. All right, so this one's working fine. So anyways, I didn't get to do that, but like I said, there is a video on there on my YouTube channel, and I was looking at last week's module, which was week 4. And week 4, I put it's supposed to be chapter 24. For some reason it says chapter 4. Okay, but it says capacitor circuits, inserting a dielectric slab and pulling a capacitor apart. You can see all of those are decent videos. RC discharging, RC charging, that stuff we're actually going to do this week, but it's already on chapter 4, so I'll move it down to here. But anyways, I just want to make sure you guys know that that is available to you. Again, if you want to look for a particular video for this class, remember it's always labeled 242. So you can just do a search in my YouTube channel for 242, and that'll give you all the videos I've made for physics 242. I've got other words in there that you can find, but the 242 is always get you to this class. So we got another student now. All right, so I'm going to go ahead and start with chapter 25. And I'm going to start off by reminding you that how we used to have to, I say we, they, well before my time. So in the 1800s up through the early or the late 1800s and maybe even the early 1900s, we were trying to hash out what electricity and magnetism was telling us. In fact, Maxwell had actually more or less solved the problem. With early only adding one major contribution or maybe 2. Michael Faraday had basically done everything else. A lot of other people, of course, Galvani and Oersted and all these other people, Faraday had done a lot of things, but probably Faraday was the big contributor. And it was kind of a cool story just because of his lack of a college education, and just his whole story was really awesome. And he basically had written a notebook from all of his experiments, where basically when James Clerk Maxwell got the position as the occasion professor of mathematics at Cambridge, he was able to just read Faraday's book, translate the language to mathematics, and basically had Maxwell's equations, except for one part that seemed inconsistent. And in fact, he fixed that. And when he fixed that, we got what's now known as Maxwell's equations. And they were in a quaternion form, which was ugly. He had also did some things which were the fashion of the time, which was trying to make mechanical analogs to what the electric and magnetic field would do. So if you want to think about that, you can imagine that basically like a donut. So if you had like a magnetic field going through the center of the donut, then what would happen is that magnetic field would create a current going around the donut like this and all those places. Or alternatively, if you had a current going through the center of the donut, that would create magnetic field going around this way. So there's all sorts of weird things mechanically, and it's kind of hard to work out. You have to sort of think of a donut with donuts wrapped through its middle, and that's ultimately what it gets. But in that way, you can sort of see how there's sort of a gear-like representation of the electric field, because it turns out like when the magnetic field is changing through the center of the donut, then the electric field is now making circles around it, weird stuff like that. So it's really a kind of interesting thing, but he was actually taking the task for that. And the language of quaternions, which was created by a guy by the name of Hamilton, who was a great mathematician and thought that his quaternions was his best invention. It turns out that wasn't very good, but he still has it on his tombstone. But no one really understood quaternions. Not a lot of people understood quaternions, so it got no credit. And of course, Maxwell died of a horribly painful stomach cancer at a very young age, just like his mother had. And it was a bad case because he went down in history, at least during his lifetime, as sort of somewhat of a failure, which is sad because later we figured out how brilliant he was. He was the first person to explain to us what the rings of Saturn were, and he basically worked it out where it had to be particles. So he did that. He had worked out the statistics of atoms and molecules, and he was right about that. And he had actually written Maxwell's equations completely correct, but no one really paid much attention to that because it was so complicated. But it turns out there was a guy by the name of Oliver Heaviside and a couple other guys who historians have named the Maxwellians, and they sort of did the cheering for Maxwell. And Oliver Heaviside was another one of those persons that had very limited education because of his poverty. So he didn't get to go to college, but he outscored everyone. Like when he was, I think, in 6th or 7th grade, he had the maths test, which decides whether you're going to college or not. And he scored like the #1 spot in that test, but he had nowhere to go. So it didn't matter too much because he was too poor to go to college. But still, he got a job with the company that was trying to basically run a cable from Great Britain to the United States. And he became somewhat of an engineer on that. He could pick, where faults were in the line that they were laying across the ocean and stuff like that. And he realized he was very good at it, and everybody knew he was very good at it. But there were some arrogant people that didn't want to give him anything because he, had very little education and stuff like that. So he said, "Screw it! I know what I'm worth. You don't know what I'm worth. I'd rather not work for someone that doesn't know what I'm worth." So he literally lost everything. He quit his job and went and moved in with his parents. But then he spent the rest of his life writing papers and writing articles and explaining how electricity and magnetism works and selling the nation and all the world, in fact, on Maxwell's equations by rewriting them in the form of vector calculus, which he and I think the guy's first name is Stephen Gibbs, an American from Gibbs Free Energy. Those two guys invented vector calculus in that time, and that was really what made Maxwell become famous, because vector calculus is so much easier to understand than quaternions. So he did that. But in all that time period, they didn't really have a mechanism by which they could get any amount of charge and have it flow continuously or anything like that. All they could do was sort of spasmodically make a charge and then expel it all at once. So you could, the typical thing we would do now is you could take and rub your hair on a balloon, and then you could take your hair and put that on a Leyden jar, and that would basically was a capacitor, but it was a capacitor that would hold the charge for a certain period of time. And then when you touched wires on it, that would take all the current away at once. But a guy by the name of Alessandro Volta had been working with dead frogs, and creepily enough realized that, oh wow, that dead frog's leg just twitched. And some people thought that might be the signs of the soul. That didn't turn out, and he didn't think that was the case. He thought it was going to be something chemical, and ultimately he did figure out it was something chemical. And you can make, muscles twitch to this day just by putting electric shocks on them. There's various things they do for conditioning, or for preparing women for childbirth and stuff like that. They can put these little basically pads on you and run electricity through it, and it'll make your muscles tighten and loosen and tighten and loosen. So he can still do that to this day. But what he realized was really it was sort of two dissimilar metals. In other words, two metals that weren't made of the same stuff. and as long as they had a connection to each other via some kind of aqueous solution, specifically one with electrolytes in it, then that could generate electricity. So he created the first what would be called a battery of piles. Okay, so they called it piles for a long time, or pile, and ultimately became battery as well. But basically what his battery was, and your book has a drawing of it from the 1800 paper as well, so that's kind of nice to check out. But I'm going to draw it for you and sort of explain what's going on. So let me start by sharing my screen. Okay. Of course, it's going to say it couldn't. I thought I'd fix the problem where it would first say I couldn't check, but I have not evidently, because it did it again. That was not what I want either. Darn you. There it is. Okay. So I'm going to do this. I'm going to turn my Wi-Fi off again. Sorry about that, everybody. Turn my Wi-Fi on again. Try to connect my iPad again. And this time it works. Okay. So if you look on in the book, you'll see a stack of basically zinc and silver plates. So what you do really to make a battery is you could take and say solder a little bit of wire to the bottom of, say, a zinc plate like he had. So this would be zinc, say. And then you take a little bit of moist cloth and in principle, that cloth, a thing that could be really good would be, for instance, lemonade. It could be an acid, it could be a base, and it could be anything but just about distilled water. That's probably about the only thing you don't want it to be, because distilled water has very little electrolytes in it. That's also why it's dangerous to drink distilled water as opposed to regular spring water or fortified water. So now this part's just a wire soldered to the bottom. Okay. And now you take and put an aluminum slab there. And it turns out that if you take another wire and put it there, what you have now is a single pile. And that gives you about 0.7 volts. I think your book tells you that it turned out when we got better at measuring this, it was more like 0.7, I think 3 or something like that volts. But this is what Alessandro Volta had actually measured, was that it was about 0.7 volts. So that was pretty good, because for starters, we were measuring voltage very well. And at the time, the best electroscopes that were made basically would just 40 volts would cause 1 degree of deflection of a little metal tab, if you will. So the typical electroscope might be said to be made like this, where you'd have let's say a Planter's peanut jar, and you have a little piece of copper wire sticking out of it. Then the copper wire comes through the jar and has a little hook on it like this. Okay. Now, because that wire is copper, it can take any charges it gets and runs them down to the bottom. And that hook's just getting worse the more I draw it. So, let's scribble on it now instead of erasing it. Okay. So this little wire is going to come down and have a hook. And you hang sort of a blade of aluminum foil and another blade of aluminum foil next to each other. And when you apply a charge to that, the blades will deviate outward that way. If you apply more charge, they'll get farther out like that. Well, this was 1 degree at 40 volts. So they couldn't measure very well, but because of what Volta had done, he had actually managed to find in some sense, a physical, electrophysical body that could do better at detecting voltages. And of course, he was measuring on the order of 0.7 volts. But they realized that 0.7 volts wasn't really that good. So what you do then is you say, okay, well, let's put another piece of cloth up there instead of the wire. Dang it, just turned to eraser automatically. So let's put another piece of cloth up there instead of the wire and the solder, and then put another piece of zinc, and then put another piece of cloth, and then another piece of silver. And now the voltage from here to here is 1.4 volts roughly. And obviously the idea was the more you stack them up, the higher the voltage you could get, and you could basically get any amount of voltage you wanted. Now, ultimately, that's sort of what we do with batteries, but nowadays what we do to make a battery is we take basically a zinc cup and we take a carbon rod, which if you're a Simpsons fan, you will know that the carbon rod, in fact, won Employee of the Month at Springfield Nuclear Power Plant before Homer did. So that's something. Okay, so this is a carbon rod. And that is the anode. And this is the cathode. Okay. So now you backfill all this, which is basically a circular collection of paste with a hole down the center, with electrolytic paste. Now, in principle, you could just do it with, say, a alkaline solution. That's where we get the idea of the alkaline battery from, is you fill it up with the opposite of an acid, specifically a base. So you might think of various soap products mixed with water, or you could fill it up with an acid. So you could think orange juice or something like that. But we found over time that between universities and companies, corporations, and lone scientists, probably the best way is put this electrolytic paste in there. Then you put a little plate that is an insulator. So an insulating plate that actually keeps the carbon rod from touching the zinc and also caps off the electrolyte from coming in. And then you put a metal on top of that just to hold it more secure. And you put another metal on the outside of it. And by doing all that, you're able to actually make a positive anode and a negative cathode at the bottom. So the anode is positive, the cathode is negative. And that's a modern battery. And modern batteries like the AA or the AAA or the C battery or the D battery, all those guys are just basically V equals 1.5 volts. And in fact, when you first buy them, you'll get like 1.72 volts or something like that. What it is they give you a little bit more because your design plan will always assume you've got 1.5 volts coming out of the battery. And as long as the battery is still good, it will be able to produce 1.5 volts. But as it gets older and older and older, it appears to be unable to produce as much voltage, and it'll sink below 1.5. And we model that by putting an ideal battery that never goes dead in line with a internal resistance. And then that internal resistance increases over time. And that's what makes the voltage at the terminals get smaller and smaller and smaller. So the way you use batteries like AA's, AAA's, C's, D's is you almost always stack them on top of each other. So you have like a AA battery like this, and then you stick another AA battery on top of it like this. That's because your power source needed 3 volts. Sometimes it'll have that, and then it'll have a wire running from there, and you'll have the negative end. So this is positive and this is positive. You have the negative end of this one up and the positive end down. And then again, you have the negative end of this one like that. Well, that's because it needs 6 volts. And by connecting the battery across there, you did the same thing as if you stack them on top of each other. So a lot of things that you use day in and day out will have batteries that are put in series like that. And what they're doing is trying to build a bigger and bigger voltage. If they put them in parallel, that means whatever voltage they decided on, they could put two in parallel with each other. That would mean 1.5 plus 1.5 on each leg, and that would be a 3-volt power supply. But each individual set of batteries only has to supply half the current. Or you could do 4 across, and then each of the pairs of batteries would only supply a quarter of the current. So that's the kind of thing you can do. And you can even connect them backwards where positive is forced against positive, and that's what you do to charge a battery. So your book talks a little bit about that, and that's an interesting thing and something you need to have some knowledge of just for everyday life. The main thing, though, is batteries that aren't rechargeable, they're still somewhat chargeable, but there's a high danger that they could catch fire or get too hot and explode or something like that. So if you really wanted to charge them, like maybe you're stuck out in the wilderness and it's the only batteries you got, you could actually charge them with a power supply, but you need to put it like on a timer or something where you maybe charge for 30 seconds, wait a minute, charge for 30 seconds, wait a minute, charge for 30 seconds, wait a minute. And that might even be a little too fast. You'd have to keep checking and see if the battery is getting hot. But in so doing, you could ultimately charge even the unchargeable batteries. It's just, it's something that you only want to do if you have to, because of it's a dangerous situation. So that's how it is. And now all of a sudden, in light of me telling you what a battery or how a battery was made, it probably makes perfect sense that the symbol for a battery is a short line, long line, short line, long line. I've even seen them go up to 3 pairs like this before. And the long side is the positive and the short side is the negative. You don't have to do that many. In fact, it's perfectly fine to say short line, long line like this, and that too is a battery. Okay, but I really like it because you see in that diagram on the left really makes you feel like, oh yeah, that's exactly what it is. 2, different metals, and you can think of their electronegativity, if you will, or their ability to steal electrons or suck electrons up is indicated by sort of the length of them. And so that would help you understand why zinc and say silver are 2 different things to use. Okay, and technically, by the way, this if I remember correctly, the symbol for silver is Ag. Okay, I just wrote A up there because that's what they had on Volta's diagram. And now that they have that, they can actually produce continuous flows of charges, which is what a current is. And in fact, I will tell you that a current is the amount of charge delta Q that passes a particular point in a wire in a time delta T. That is essentially what we call the average current, which also could be written by as AAVG, or it could be written as I in those brackets, because those are all symbols we use for average. And just like we did with velocity and acceleration, you can imagine the instantaneous current would be the limit of this delta Q over delta T as delta T approaches 0. And that, of course, becomes dQ over dt. Okay, so that is what current is. And you've probably already experienced in lab, but there's a law that relates current and resistance, and it's called Ohm's law. And Ohm's law says that V is equal to IR, which means several different things. One thing you can say is certain objects in the universe are what we call ohmic. So ohmic devices. I don't know why I wrote a devicer there, but I did. Okay, so certain things in nature are ohmic devices. They're devices whose resistance is a constant. So it implies R equals a constant. Okay, and R is called the resistance, and the unit of R, as you can tell, is the volt per coulomb per second, because it turns out, as you can tell, the unit for current is, of course, coulombs per second. Well, this unit, which is also equal to a volt second per coulomb, is also equal to what we call omega. Okay, and that's called ohms, named after this gentleman, Ohm, but also given the Greek letter ohm for omega. Okay, so it's actually omega. And that's the symbol that we use for it, is the Greek letter, like I am the Alpha and the Omega that you hear in the New Testament, or even, well, actually it's in the New Testament. And that's because the New Testament was written in Greek, and Alpha is the first letter of the alphabet and Omega is the last letter of the alphabet. So that's what that is. Now, another way to interpret Ohm's law is that if you plot voltage on the vertical axis and current on the horizontal axis, then at any point, the slope of that graph would be the resistance. So we might have, for instance, an object that makes a line like this, and the slope, which is rise over run, which you can see the rise is clearly in units of volts and the run is clearly in units of coulombs per second. That might be, say, 200 ohms. Then there might be, say, another one that has M equal to 400 ohms. And then there might be yet another one that looks like this. And I think you probably graphed one sort of like this, in which case the slope is one thing here and another thing here. Okay. So that's another way of interpreting Ohm's law. Ohm's law is a way that tells you you can put a number next to the I and multiply those two, and that should give you the voltage drop or gain by going across that object. So that's another way of interpreting Ohm's law. So those are equations you definitely want. So I'm going to box them off. And I made sure I did it with a different color. Okay, so now we know the current, we know the Ohm's law. What I want you to think of now is, let's imagine a chunk of wire, a chunk of conductor, if you will, that we're going to use to make charges go down. Okay, so let's say I have a wire that looks like this, that we want charges to flow down. And you can sort of think of how easy it is to go through this thing as the inverse of the resistance. The resistance is supposed to be higher the harder it is to get through. So which one of these looks like it would be harder to make it through? And you can also think of it as harder means it takes more time. That might help. High R sort of implies takes more time. That's one way you can think of it. Or energy is another way you can think of it. Okay, so which one of those, the left one or the right one, do you think it's easier for charges to go through? They're both supposed to be the same size, diameter for starters. And you said which one?
Assuming they're made of the same material, the right one.
Yeah, same material too. So the one on the right. So you expect R to be larger for these two, just because you can imagine it like I got to take 1 million charges through there. Well, it's going to take a certain amount of time to walk through there, and I got to do that 1 million times. So it's clearly going to take more time because I got to walk through that whole long distance. So from that, we reach the idea that R is proportional to the length. Okay. Now let's say we take two wires of the same length, but of different cross-sectional areas. Which one of these would be the largest resistance, or would take the most time to get, let's say, a bunch of old people through it?
That small one.
The small one, right? So this one is our largest, or larger. So this implies, and you might not see it this way immediately, but this implies that the resistance is inversely related to the, let's say pi r squared r1 over the area. Does that make sense to everyone? Because really it's that cross-sectional area that matters. Just that's why I tried to say about old people, if you have a narrow little tube you got to fit them through, then you're probably gonna have to lay them down and then push them through head first, and they're gonna have a panic attack in that situation. But if you make it a bigger diameter, then you could probably have 3 or 4 walk abreast. You might even be able to build a floor, a third of the way up and walk another set, and then another third of the way up, walk another set, and you can get 3 by 3 by 3 going up there. So yeah, that bigger one allows a lot more people through. Now that really is geometrically how the resistance turns out. What we found out from just that little excursion was that R and L are thumbs up, thumbs up. The longer the wire, the more resistance. What we also found out is that the bigger the radius, the smaller the resistance. But in reality, we didn't determine whether it's R proportional to L squared, or R proportional to L cubed, or R squared proportional to L cubed, or anything like that. And the same thing with the area. We didn't say it's R is inversely proportional to A squared or A cubed or anything like that. But it turns out we were lucky that's exactly what it is. So the ultimate result is geometrically, we only have to take into account the L and the A. But you can think of a constant of proportionality, if you will, as something called the conductivity. Excuse me, resistivity, I should say. I got the conductivity on my mind because it's so funny. I like the way they measured conductivity in mo's, which is, OHM spelled backwards as a mo. So I like that. But anyways, that's the resistivity. And that's a property of the metal. Your book has a table of it, of them. And of course, that means if I ask you a problem to calculate the resistance of a wire, I have to supply you with the resistivity, or I have to supply you with a table of resistivities, and then I have to tell you what the material is. So for instance, the resistivity of copper is 1.68 times 10 to the negative 8th. Can you guys guess from this formula, rho L over A, what the units of rho would be? Anyone? So you've got to get an ohm out. So there's an ohm in the numerator as a unit there. You also have to get rid of a meter that's in the top. So you might think put a meter in the bottom, but then you'd realize you need a meter squared in the top to get rid of the area. So meter squared over meters just gives an ohm meter. So that's what the units are for omega. So let's take an example. So the distance between the Earth and the sun is 4.23 times 10 to the 7th meters. Excuse me, moon and Earth. I think it's a moon and sun. Is about 4.23 times 10 to the 7th meters. What is the resistance of a copper wire that long if its diameter is, and let's say its diameter is going to be a whole centimeter. So that's a pretty robust wire. I'm thinking that might be like 10 gauge, maybe 12 gauge, something like that. I want to say 1.00 centimeters. Okay. So that's our question. And I don't usually work a lot of these problems, if any, just because they're so straightforward, but I figured it might be good to see one because I'm going to constantly make the argument that wires have such a little resistance, you can usually ignore their resistance. So here's the solution. So R is equal to rho L over A, which equals 1.68 times 10 to the negative 8 ohm meters times the L, which is 4.23 times 10 to the 7th meters. All of that will be divided by pi times 0.500 times 10 to the negative 2 meters. And that'll be squared. In other words, I did divide 1 centimeter by 2 to get the diameter. I mean, to get the radius from the diameter. So that's the key thing you watch out for. And that's the most common mistake is people will see the diameter and think of it as the radius, and that's just wrong. So I'm going to do 1.68 e to the negative 8 times 4.23 e to the 7th. And then I'm going to divide that by parentheses pi times 0.5 e to the negative 2. And I'm going to square that part. And then I'll close parentheses and get the answer of 9,048. Which evidently it wants to make an eraser again. That's so helpful. So 1,048 ohms. So that's really just 1K. And by the way,
9,000.
What's that? Or excuse me, 9,048. Yeah, thank you for catching that. So 9048, sorry about that. And actually this one's not even a sig fig, so we technically should write this as R equals 9.05 times 10 to the 3 ohms, or 9.05 kilo ohms. So that's literally a chunk of wire that is the length from the center of the moon to the center of the earth, and still it's only a 9 kilo ohm resistor. We deal with mega ohm resistors all the time. And in fact, unless we use at least kilo ohm resistors, we're going to consistently get whole amps instead of milliamps, which we like working in the milliamp world for most things. Some things you just have to work in the high amp. Like if you're wanting to weld something, you need on the order of 150 to maybe even, depending on how thick the stuff is, maybe even 350 amps. But it only takes a milliamp to kill you. So it's best to work with low amperage as much as you can. So that's one of the expressions we got. So we now know a new equation that can come in handy. And that's rho equals L over rho, R equals rho times L over A. Now, another thing, another property of a wire is that, in fact, because the wire is just a chunk of metal, and if it's a conductor, what that means is each atom in it has an electron that's not tethered strongly to its atom. So it usually has at least one electron that's free to move about the entire metal. And when you actually apply electric field to that, which is what a battery does, you apply electric field that goes along the wire. That electric field compels the electrons to move in the direction opposite the electric field technically, but we pretend like it's positive charges. So we think of positive charges moving in the direction that conventional current flows. But as the temperature gets higher and higher and higher, the atoms are jiggling way more erratically, and electrons are getting frequently stopped by bumping into particles and stuff like that. You can think of it as positive particles are getting bumped, but the main thing is, at the end of the day, it's going to be more resistant at higher temperatures. So one way you can interpret that is, I think I can fit it all in here without any problem. So I'm just going to write it down here. What we're going to say is that a change in the resistivity, rho, is proportional to a change in temperature delta T. Remember, delta always means final minus initial. So this isn't the form we normally use it in, but I think it's useful for you to see it that way, because it turns out also you can say delta R is equal to alpha delta T as well. So that's another one you can use. But the big thing is they normally don't use it this way. They normally say this is rho minus rho zero. That's what delta rho is. And that's equal to alpha times T minus T0. And that T0 could be a temperature of 0 Celsius if you wanted it, but it doesn't have to be. And the rho zero would be the resistivity it had at T equals 0 Celsius. But again, it doesn't have to be. You could look in a table and maybe you're working with a wire that you know consistently is close to 100 degrees Celsius. If that's the case, then you try to look for the rho zero that's closest to 100 degrees Celsius. Maybe you found one that's 85. So your rho zero would be the resistivity at 85 degrees Celsius, and the temperature T0 would be 85 degrees Celsius. And then you just do 100 minus 85 and solve for P, which gives you this equation, which is the way your book does it. It says rho is equal to rho zero times 1 plus alpha, I'll make this a square bracket, times T minus T0, close the square bracket. So that is the equation that your book gives you, but it really is the same as that initial equation. Actually, that was really bad because it covered up everything. Okay. Okay. Now, similarly, you could also say that R is equal to R0 times 1 plus alpha T minus T0 as well. Okay, so these are pretty straightforward equations to use. I think you'll readily be able to use them when the problem asks for it. So you know, hey, if they're talking about how's the temperature changing the resistance, you're going to use one of these things. You can either do it in terms of the resistivity or you can do it in terms of the whole resistance. But that's just another equation that we need to be able to solve some circuits and stuff of that sort. Any questions on that? Uh-oh. Hold on. I'm trying to move this stupid Zoom window. And I didn't mute myself. I thought I muted myself for a second. All right, so I guess I'll move this window instead. So that basically brings us all the way up through resistivity. And now we're at the point where we want to know electric power. So recall from earlier that power is often dW over dt, or it's the amount, R it's the amount of energy over dt. Okay, so this is energy, not electric field. But we also know that occasionally delta W is actually equal to delta U, or normally the negative of it or something like that. Well, we did learn that delta U is equal to Q times delta V. And in fact, that was sort of our definition of voltage is the potential energy per unit charge. Well, we could also say that delta U is equal to V times delta Q if we wanted, because that's just the way differentials behave. So if we do that, we can say, oh, well, P, which is equal to delta U over delta T, are actually instantaneously is going to be du over dt. Well, that can be written as dq over dt times v. Well, dq dt, of course, is just I, so that's IV, and that's one of our famous equations, P equals IV. Now, the one that's more helpful is when I try to eliminate the voltage. So I can take Ohm's law, which is V equals IR, and eliminate the voltage by replacing the V with IR, and I get I squared times R. That one's really helpful, and I'll tell you why in a second. Now, I could also get rid of the current in the first expression by using I equals V over R from Ohm's law, in which case I get V squared over R. So all of these are different forms of the power that is the power that is emitted, if you will, from an electric wire of resistance R carrying a current I or a voltage V. Okay. So what that is literally just heating up. So when you run a current I through a wire and the voltage from one end of the wire to the other is V, then IV joules per second are actually, or watts, are being wasted to heat that's going out into the atmosphere. Okay, so that's what that means. Now, the reason why that second version is so important is basically a house requires 200 amps of service. Okay, every house. That's the general rule. Like if you go in a neighborhood or a state or a city or anything like that, you'll find that there's some basically a covenant or law or something that dictates every house gets a 200 amp service. They can get more if they want, but basically what they do is assume that you're going to want 200 amps and they're going to send that to your house. So if you have a power station like this, and that's going to feed a neighborhood then I knew I wouldn't fit that in there. It's going to feed a neighborhood of, let's say, 10,000 houses. That's a big one. Okay. Then what the power plant has to put out has to produce and this is the power plant, by the way, it has to produce 200 amps per house times 10,000 houses. Okay, so that equals 2,000 times 10,000. That's basically 2 million amps. Okay, you can't get over that. That's just something you have to do. No ifs, ands, or buts about it. Now, you know the resistance of the wire is given by rho L over A. And in fact, a lot of these wires that you see going for miles and miles across crunchies and mountains and country fields and stuff like that, they're usually made of aluminum, not copper, because aluminum is a lot cheaper. Okay, so we're going to have a rho due to aluminum, say, and we're going to have a length that's fixed to a number of miles to the house, and we're going to have a equals fixed, and we're going to have a set diameter wire that's fixed as well. Okay, so no matter what, there's a set resistance that you're going to have to deal with just because of how long the wires are. It's not going to be that big of a deal because the wires, you know, as we showed, even a wire running from the center of the earth to the center of the moon would only have about 9K or 9 kilo ohms of resistance. But that R is fixed by basically the amount of wires you need to go from the power station to the neighborhood and then into each individual house. And that can't change. Okay. Not only that, because that resistance is set, we know, well, I'll go ahead and write this. So R is fixed. But not only that, by Ohm's law, that implies that V is fixed as well, because I'm sending 200 amps for each house, which gives me 2 million amps. So 2 million amps times whatever that resistance is going to be fixed as well. So there's really really no room to play. You can't change V and you can't change R very much. I mean, you could change from aluminum to copper, and the cost of copper would make it more expensive, but you would be saving some energy wasted because the R is smaller. But it's not enough for necessarily power companies to do that. That's why they run so much aluminum on high wires. So those two quantities are fixed. That means the only thing you really have to work with is either IV, and you have to know the distance so you can figure out V, or I squared R, which you have to know the distance so you can figure out R and the radius and all that stuff. So it turns out that power is proportional to the square of the current you're sending. So it's proportional to 2.00 times 10 to the 6 amps squared, which is of course 4.00 times 10 to the 12th amps squared. So you're going to waste a buttload of energy by driving that over there. Well, what do? Well, it turns out that there's things called transformers, which I tell my students, it looks like the Pilgrim's belt buckle from grade school. So almost everybody did some kind of Thanksgiving Day parade, or play at school, and inevitably there was some kid wearing a belt buckle that looked like this, right? So if you actually took a chunk of iron and made a belt buckle like that, and then you took the wire coming from the power plant, from the PP, okay, and that wire came in and wrapped around this, let's say it wrapped around it, let's say N times. Okay, now you took this wire and ran that to the neighborhood. But this wire had N turns, which was in fact, let's say it was 10,000 times N turns. Well, it turns out you're going to send this out at 120 volts. That's what's going into there. Well, it'll come out now 120 volts times 10,000, which equals 120 times 10,000. That'd be 12 times 10 to the 5th. So 120,000. So that's 1.2 million volts. Okay, so the voltage is being stepped up, but it turns out when you use a transformer to step up the voltage, you can think of the power can't change, so I times V has to remain the same. So if V went up by a factor of 1.2 times 10 to the 6, then the I goes down by 1.2 times 10 to the 6. So P in equals P out is the best case scenario. That's 100% efficient, 100% efficient transformer. So that would mean 120 volts and 2 times 10 to the 6 amps has got to equal, we just found that 1.2 times 10 to the 6 volts. That's going to be how many amps we have left. So this would be I out. So I out is going to be basically 120 times 2 times 10 to the 6 divided by 1.2 times 10 to the 6. And yep. And in fact, yeah, that's right. That in fact is going to make the amperage go down considerably. 2 divided by 1.2 is the same thing as 20 divided by 12. So that's 1 time with 8/12, which is it's 2/3. So 2/3 is what that answer is there. And then times 2 would be about times 120. That'd be about 40. This would be about on the order of 80 some amps or something like that. You can actually do the math yourself. So I'm just going to say that because I probably did some arithmetic error, but about that. Now, what we've done is taken the amperage and gone from 2 million to on the order of, actually, it might be on the order of 800, not 80. Sorry about that. But y'all can check it yourself. Now, because of that, the power loss has went down by a factor of, remember the factor turning out to be 2, or 1.2 times 10 to the 6, it's actually gone down by a factor of 2 million over 10,000. And that number is squared. So that's why the power companies use such a high voltage going from town to town on those towers that you see that sort of look like a person, but without a head. Right, it'll go like this. Those towers are sort of the ones that carry the wires. So those things are actually on the order of hundreds of thousands of volts, if not millions of volts. And in fact, they're so dangerous that even like if a mountain happens to be in between one tower and another, you get so close to the wire that I've actually walked under them or ran under them. I used to run in the mountains quite a bit, and you could hear electricity popping because it was ionizing the air between the wire and the ground, and little lightning strikes were basically leaving the wire and hitting the ground. That's how high the voltage was. So and then during the rain, it's really crazy. You hear it a lot. But anyways, they do that, and that allows them to save a butt ton of money. And in fact, then they run it out there like that in the middle of the field. If it's out in the middle of a country field or mountains or something, some wiseacre could actually come out and build, say, a really big loop of many wires. And it turns out that Faraday's law actually would allow us to steal electricity that way, because that wire is making a magnetic field that sort of rolls around the wire like my fingers are rolling around this pin. So the pin's like the wire, and there's a magnetic field going around this way, and that field is changing from going this way to that way, this way to that way, 60 times every second. And by going through that wire, you're actually producing a voltage difference from one end to the other. And in fact, you can just, power up your battery, charge your car battery, run a stove or whatever. But the power company knows about the science. So of course they can really tell within a matter of minutes what area you're doing that, and that's happening. Because for every bit you're stealing, they're losing probably about 10 or 15 times as much, because it's not that efficient of a process. So anyways, in this sense, we've now gone over power, and we've even gone over transformers, which we'll talk about later. You'll see the actual transformer equations later, but basically a step up transformer is when you go from a small number of turns to a large number of turns, and that steps the voltage up, but it also steps the current down by the exact same factor. And that's 100% efficient. Now, they aren't really 100% efficient, but like Dominion Power and Duke Energy and all these companies, they've sort of maximized the efficiency of these things. And now you'll see them, they look like a little bit bigger than 5-gallon buckets up at the top of a telephone pole. And they'll have something like this, Pilgrim's belt buckle up there. It'll actually be made in several little plates that are shaped like that, and they're all sort of glued or welded together. And then it'll be submerged in often some carcinogenic oils, and all that makes it act more efficiently and allows the heat to be dissipated. But they'll basically run it at that high voltage straight from the power plant. It'll go to 200,000 or even 1,000,000 volts. And then it'll come down to a substation before it goes to the neighborhood. And the neighborhood normally will receive from the substation basically a voltage on the order of, I think my dad told me, 36,500, maybe down to 15,500, something like that. That's the stuff that's rolling overhead through a neighborhood or from one neighborhood to the other. And then as it goes to your house, it's knocked down to 3 120 volt AC signals. The 3 are each 60 degrees apart. And if you plug the top one, the first one, say, with the last one, then you'll get a difference of 120 plus 120, and you'll actually basically get a 240. And that's how you run your dryer. That's how you run electric stove and some other things that take really high voltage, 220 volts. If you go to Great Britain, or if you go to many places on earth other than the United States, they often run 220 volts or 240, actually 240, excuse me. They often run 240 volts, and they also don't run 60 hertz, which is what we do thanks to Tesla. They normally run 50 ohms and 240. So we run 120, but it's triphasic, so that we can use the first 120 and the third 120 to get a difference of 120 plus 120, which is 240. That allows us to fulfill the need for 240, but still only have to carry 120. So that's a lot of words. I'm just giving you some technical details about how this stuff works. Now that I've gotten through that, and you can see how to use these equations, I've sort of hinted at it, and I've also shown you some stuff. I've now discussed power. What I want to show you next is, in fact, how houses are wired. So if you look at your receptacle in your house, it looks like this, and you'll have a circle. And if you had a really good electrician, and this is somewhat of a opinion, like some electricians do not necessarily consider this as better than the other way. I personally do from a safety standpoint, but what you have is one big side and one little side. So it looks like he's a little drunk or something with a mouth, right? And then you'll have another one just like that, like this big side. And I might have the big side on the wrong side and the little side on the wrong side. But the main thing is, you know, that there is a difference. And in fact, when you buy the receptacle, the thing behind this plate, there's a little screw here, for instance, you buy the thing behind the plate, it looks like this. And there's the little hole, if you will. And there's the little hole, if you will, the big slot, and the little slot, and the little slot, like that. What you'll see is there's a screw right here, and there's a screw right here, and there's actually a lot of stuff on it. There's little holes in the back that you can plug the wires into. These, if I remember correctly, so I'm going to put question mark gold, question mark. It's basically gold goes with one of the slots and silver goes with the other. And if you actually open the receptacle, it'll tell you that. There's another screw over here, and these are just silver. And again, I might have it on the wrong side, but the main thing is one's going to be silver sided and the other one's going to be gold sided. And then there's probably somewhere where you'll have like a green screw, let's say like right here. And that's that little guy, okay? And it would have been smart of me to write that in green, so I'll do it now. So that's what a receptacle looks like. Now, the way you wire that receptacle is you have a wire that is in a housing like this. And out of that wire comes a bare wire. And out of that wire comes a black wire. And a white wire. Actually, let me make this one green just to have a different color. And this wire will be white. So again, I'm using my memory here, so I don't want to stick you to this. But if I remember correctly,
there's also a red.
Yeah, sometimes
if there's no conduit, there's a green.
Yeah, and sometimes you have runners that go from one switch to another, stuff like that. But yeah, sometimes you will have 4 wires in that same thing. That's a different story. But if you're wiring something and it just comes up with these 3, and I'm trying to use my memory. If anybody knows off the top of the head, by all means, correct me. But if I remember correctly, I think the black connects to the gold.
Yeah, black goes to gold,
White
goes to gold,
silver.
white goes to silver, green goes to green.
Thank you. Silver. And the bare goes to the green ground. And you said the red goes to the silver as well?
Red goes to gold. Red and
Okay.
black are both hot. They're just different phases.
Yeah, that's what, okay, that's cool. So with this one, the bear is just going to go to the green. Okay. And like you said, there's sometimes will be a red wire in there as well. And you said the red and the black are both hot, but the white's supposed to be the neutral, right? Is that, am I remembering that correctly?
Yes, that's true.
Okay. So when you go to connect them, you'll see that you have a white wire and black wire. And then you can connect to the other screw like this, and this will be black, excuse me. That'll connect to this screw, and the white will connect to this one. And that keeps on for over and over and ever for every receptacle on the given breaker. Okay. The reason why I'm showing you that is you realize that this is basically like, here's the white wire, here's the black wire, and here is something that you plugged in. And here's something else that you plugged in on that same circuit. And here's something else that you plugged in on that same circuit. So you see that the actual electricity, the outlets are run in parallel. And that's good for a couple of reasons. And one of them being, if you ever were old enough to ever experience the cheap Christmas lights, basically there was one wire that would run to a light bulb, and then a wire would come out of the light bulb and go to the next light bulb. Well, the light bulb basically takes charges that come into it, and they go through a piece of tungsten usually, that instead of getting so hot that it melts, it just gets hot and glows. And then those charges leave the glowing part and go out the other hole and then come into the next one. Well, if your light bulb burn out, that means that tungsten broke in half, and you've now opened the circuit, so none of the lights will work. If you put them in parallel, that wouldn't happen, because all that happens is, oh, now I'm just in parallel, but I removed one of the resistors. So that's one reason. Another reason, of course, is that voltages in parallel are all equal. So each of these will in fact be the 120 volts, which is technically not really what it is, because the real voltage as a function of time actually looks like this. It's AC, and it goes from negative I0 to positive I0, and why am I switching to current all of a sudden? It goes from V0 to negative V0, and it turns out that the V0 equals 120, or the V equals 120 volts, is actually V0 over the square root of 2, which is called the VRMS. So you might say voltage is equal to V0 times sine of 2 pi F times T. This F is the 60 hertz that we use here in America. And the 2 pi is just a constant that makes the sine function act the way it's supposed to. Now, what you have to do to figure out what the average voltage is, which is what that RMS is, we integrate from T equals 0 to 1 period. So that's 1 period, that's 2 periods, so on and so forth. We integrate that, but if we actually integrated that function, you see the left positive hump is exactly the same size as the right negative hump. So the answer would be 0. So what we had said and do is we take V0 squared times sine squared 2 pi F times T, and we integrate that over time, and then we divide it by T, the period. That turns out to be V0. Oh, actually, then we take the square root of all that. That's what we mean by root mean square. We took the average of the square, and then when we're finished with that, we take the square root of it so that we'll have units of volts again. And that ends up giving us V0 over the square root of 2, which is what we call VRMS. So if you call the voltage, for instance, 120, some people call it 120, some people call it 125, and it does vary quite a bit. I checked receptacles, and it'd be as high as 127 and as low as probably 119, 118 on occasion, but they're supposed to be fairly close in that. The 60 hertz is really pretty precise though. So if I took the 120 and I multiply it by the square root of 2, you see it's going to come out about 170. So V0 is on the order of 170 volts in reality. So that's some more sort of neat stuff, if you will. Anybody have any questions on that?
Yeah, where's the GFCI go in your little diagram?
Oh, okay. So yeah, with the GFCI, that means ground fault circuit interrupt. And basically what it has is a solenoid, or this is one way to make one, is you could have a solenoid, which is basically an electromagnet with an iron rod through the middle of it like that. And the bigger the current that goes through this, the stronger the magnetic field. So if I goes up, then the strength of the magnetic field, which is what we use B for, goes up as well. Okay. So what you might have is, you can imagine a little lever with a pointer on it and a flat disc right here. And basically the circuit of the wire, the circuit goes current in here, it comes out here and goes into this, and then it comes out of there. As you can see, if the voltage gets high enough though, this magnet's going to become so strong that it's going to pull this rod back here and disconnect the circuit. It's that point right here where they're touching. That's the actual contact point. So this is a way they do not only GFCIs, but they do, for instance, circuit breakers. This is more like what a circuit breaker would do. They have something sort of equivalent to it, I think, in many GFCIs now are solid state devices. So all this is inside of a little chip, so you can't really see it. But that is one way to do it. It turns out when you got a current running through two metals, they don't just readily separate very well. In fact, I know this because I made what's called an Elihu Thompson jumping ring, where I took a wire and I took it to the lathe and I did 1,200 turns and wrapped it around a piece of PVC. So we had basically some plastic polyvinyl chloride in there. And then I put a Teflon cap on each side. So it's like a spool. And then I shoved an iron rod through the middle of the PVC. And then more or less what I did was took our handy dandy receptacle and hooked this wire, boom, and this wire, boom, in there. Okay. Now, when I did that of course sent 170 volts peak to peak through there. It created a magnetic field. But if I take and put a washer on there, let's say a nice aluminum washer that looks like that in cross section, okay, that wire carrying that current is going to cause a current to happen in that battery in the reverse direction. I mean, excuse me, in that washer in the reverse direction. That's the way you can now lay your cell phone on its back, and it'll start charging because of a magnetic field created by a current creates a magnetic field some distance away. And in your phone, you'll have a coil of wires that when that magnetic field goes through there, that steals that energy from the actual air or from the magnetic field and charges your battery. So when this happens, the ring actually has a current going the opposite direction, and opposite currents repel each other. And in fact, I shot the ring off and got like 50 feet. That wasn't good enough for me. I went then and put what's called a variac in there, and that actually produced 140% of V0. And then I put this in liquid nitrogen, so that would reduce the resistance really well. And I was worried about the situation we had where I'm, more or less poking a wire in a hole. So I actually made a plug and then put a switch in it. And I was like, well, I needed a good switch, one that's going to pop off really easily, because I was afraid the metal might melt and weld. So I got a nice Morse code switch. And the Morse code switch, like this, it had a nice little plastic button. It had a little tip right there, had a little tip right here. And whenever I wanted to turn it on, I just hold that Morse code switch down. That was good. That completed the circuit. And in fact, I ended up shooting this to ultimately about 70 feet by using liquid nitrogen and amping it up. But when I did it the first time, I did it inside the building, and this metal and this metal ended up welding, and it got stuck in there. Well, that's a current going through a wire with very little resistance. So it was a buttload of current. And in fact, it probably was all 30 amps, which is what most receptacles are. 20 amps and 30 amps are what the receptacles are normally wired on. So I was taking all that current, and quickly that got so hot, it melted the PVC and started melting the vinyl or the Teflon. And in fact, it's very, very carcinogenic to melt PVC. They had to evacuate the physics department and the adjacent biology department, all because of my little experiment. But I do recommend making these. It's cool. I have one. I made it. I gave it to my old school, but I can borrow it at any time. But it's a nice little thing. It's called a rail gun, basically. This is the way I make a rail gun, but it's called Elihu Thompson's. That's HU Thompson, THO. I think it's THOMP, but it might not have the P in it. Okay, jumping ring. Look that up sometime. Elihu Thompson's an interesting character. He was a scientist that was trained as an engineer, and he was around when we discovered X-rays, and he was convinced that X-rays were safe. So he did a little experiment to prove it. You guys can go, by the way. I'm just telling another story, so I'm completely done. But I'm going to tell the story, and then I'll take questions if anybody has them. So he decided he was going to do an experiment to show the world that the X-ray is not dangerous. So he, got him a notebook and he recorded his observations. And basically, he held an X-ray tube against his finger for like 5 minutes a day, every day. And you read, like, for the first couple of weeks, as I thought, nothing's happening. My finger's no problem. Clearly, X-rays are as natural as the wind-driven snow or something like that. But after about a month, he says, I have ceased the experiment because my finger is a festering boil. And like 2 years later, it's only finally healing. So he did, in fact, determine that the X-rays are not safe. And in fact, he probably gave himself a sort of cancer in his finger, or maybe even leukemia. I don't know what he ultimately died of, but he was an interesting character. So we've now finished up through section 25. 6, but we've even talked a little bit about 25.7. We've even talked a little bit about no, I haven't done that. So about 25 and 27, 25.6 and 25.7 is what we've more or less completed. I've got some more to do in 25.7, but you guys are free to go, and I will wait for the last person to leave. And don't forget to do your test. You do have test 2 due. Those of you who missed test 1, make sure you do that. And y'all have a good night. Jack, do you have any questions, sir? I do think Jack's here. You might.
Sorry, no, I am. I just had trouble with the buttons. I don't have any questions. I'll see you next class.
Did you see any part of the notes you needed to get from me or anything?
No, I'm all right. I have all the homework done and stuff anyway, so
okay, cool.
I wanted to get ahead. All right.
All right, thanks, Jack. Feel free to email me or text me if you have any questions or need anything.
All right, great. Thank you.
You too. Bye-bye.